This is David Van Vranken, and this is our 10th lecture in the Organic Chemistry 51C series here at UC Irvine. And I wanted to start off my lecture by talking about uh, uh, an incident that came about in the late 1920s related to a syndrome called Jake leg. There was a song around that time, I think a blues song called the Jake Leg Blues, that is referring to this mass poisoning incident that had to do with this stuff called Jamaica ginger. And so let me try to take you back in time over 100 years before the 1918, or maybe after the 1918 flu pandemic, maybe not quite 100 years. And what you're seeing here are some bottles of this stuff called Jamaica ginger that I think were first introduced in the 1800s, the late 1800s. But you know, that time period from 1920 to 1933, it was prohibition in the United States. And alcohol, the sales of alcohol, and I think maybe even the consumption of alcohol for recreational purposes was prohibited. And so people who were into drinking alcohol found other ways to get it. And so if you were wandering around on the store shelves of your drugstore, you'd see this stuff sold, referred to as Jamaica ginger. And when you look at it, it's alcohol, 94%. My gosh, that's like 190 proof. That's so it's just pure alcohol that's been steeped with ginger. And what are some of the added other things that they have in there? I think it's ginger and cinnamon and cloves and other spices. Sounds pretty tasty, actually. But again, if you couldn't get a hold of beer or hard liquor, this looks like it would be a pretty decent substitute. And the problem is that some very unscrupulous, it's hard for me to imagine what would induce people to do this, but they were making this either fake Jamaica ginger extract, which was known as Jake. But I guess if you can't afford ginger or these other spices and you wanted it to look kind of thick, somebody must have come up with this stupid ass idea. Oh, let's take this industrial plasticizer, which might be a thick, goopy liquid, and add it to the alcohol so it seems kind of thick, like it's a real extract. And it seems that this is what they used. They back in the 1920s, cellulose acetate had just been introduced, or had recently been introduced as this thermosetting plastic that you could heat up and mold into things like combs or other plastic parts. But if the problem with cellulose acetate is it's extremely brittle, as are many plastics. And so when you have brittle plastics, one thing you can do is add additives called plasticizers that make them flexible so they can flex a little bit without bending. This molecule called tricresyl phosphate, and the name tricresyl comes from the fact that it's made with three cresol molecules. It's a phosphate triester. DNA is a phosphate diester. This is a phosphate triester. Why would anybody add this industrial compound to anything that people are going to ingest? But that's what they did. And it turns out that it's a weak neurotoxin. What does that mean? Weak neurotoxin. Well, just means that you need large quantities of it to cause some sort of an effect. Weak means it doesn't bind tightly. So, but when you have high concentrations, it can exert powerful biological effects, like messing up the nervous system. People who ingested this ended up with shaky legs and problems with the peripheral nervous system. Particularly sad. And so stupid people adding tricresyl phosphate to this fake Jamaica ginger extract led to all of these problems. And they ended up making people who ingested this stuff ended up with severe problems with the peripheral nervous system, maybe the central nervous system. I'm not sure where all it had an effect. Let's move on to our lecture. That's kind of sad, but let's move on to something that is not sad, but it's cool, and that's organic chemistry. Let me take you back to where we left off during our last lecture on Friday. I was introducing you to this range of nucleophiles that we're adding to carbonyls. And in chapter 20, We talked about these powerful carbon nucleophiles for making carbon-carbon bonds by adding to carbonyl groups, alkylithiums, Grignard reagents, those your old friends, the alkynyl sodium reagents from the alkynes chapter. And we always add these to carbonyls, avoiding any OHs in those reaction mixtures because they'll react faster than the carbonyl with and just simply protonate your nucleophile. But in this chapter, we're focusing on less powerful nucleophiles, mostly, for adding to carbonyl groups. I just want to remember, let me take a moment. I'm going to remember to mute everybody. Because I forgot to do that during the last lecture, and some people's voices came out on our lecture. So during this chapter, we're going to be talking about weaker nucleophiles, oxygen nucleophiles, nitrogen nucleophiles, cyanide anions, and then a weird set of nucleophiles also for making carbon-carbon bonds called Wittig reagents. And I'm trying to distinguish it to help you understand that when you add oxygen nucleophiles, what we'll find to ketones and aldehydes, we're going to need to add powerful acids to activate the carbonyls. Okay, I just left off on Friday by introducing you to hydrocyanic acid as a reagent for adding to carbonyl groups like ketones and aldehydes. And the mechanism for this, it's very hard. What you do is you take sodium cyanide and hydrochloric acid and you mix these two things together and you make hydrocyanic acid, but there's cyanide anion floating around. It's very hard to protonate every single cyanide molecule. And so the mechanism for this reaction starts off with the cyanide anions. Under those conditions, there's enough of these cyanide anions floating around that they can attack the carbonyl. You don't need to protonate the carbonyl. It's just like a Grignard reagent. When you add to some sort of a ketone or an aldehyde, not esters or amides, but ketones and aldehydes, this cyanide anion can come in and attack that carbonyl group. So let's go ahead and depict that. There we go. You attack the carbonyl group and you push the electrons up to oxygen. Get used to that. We're going to do that kind of mechanism over and over and over in this chapter. And you make this intermediate where you've now formed a carbon-carbon bond. And we have an alkoxide sticking up there. And here's our cyano group. There it is right there. And under the conditions of the reaction, it's not a step 2. We've got hydrochloric acid. We've got acids present. Now, we don't have to say whether the acid that's going to protonate this O- is HCN, but this alkoxide anion is going to get protonated under the conditions of the reaction. It's not a second step where we, and I'm just going to symbolize whatever that stuff is that's protonating this. Could be the HCl, could be the HCN that's present. We don't care. I'm just drawing an arrow pushing mechanism, so I'm going to symbolize the acidic species that's protonating it with a symbolic HA for arrow pushing mechanisms. If I asked you for a reagent, an actual reagent, don't say HA. We don't have bottles of HA in our lab. So, but for a mechanism, for an arrow pushing mechanism, it's convenient to symbolize that acidic species as an HA. And so the functional group that we get here is known as a cyanohydrin, where we have a cyano group and a hydroxyl group attached to the same carbon. And so whenever I see a cyano group and a hydroxyl group on the same carbon, I'm thinking I could have made that by adding HCN. And we make that in our reaction mixture by mixing together sodium cyanide and HCl. You can't easily buy HCN. All right. Now, usually when you make cyanohydrins, we usually transform those further to convert the cyano group into a carboxylic acid. And so let me show you a 2-step procedure here that involves cyanohydrin formation, followed by a hydrolysis procedure that kind of doesn't belong in this chapter because we're going to tell you more about that. So remember our conditions for cyanohydrin formation. I take sodium cyanide and HCl, and that converts this carbonyl, the ketone or the aldehyde, in this case it's a ketone, into a cyanohydrin. I'll just write CN there, kind of like a typewriter text version of the cyano group. And now there's this secret transformation that belongs in chapter 22 instead of chapter 21, but the book feels like they really want to tell you about this now, so why not? The conditions for this hydrolysis reaction, we're going to hydrolyze that CN triple bond into a carboxylic acid functional group. And this functional group pattern with hydroxyls right next to carboxylic acids is actually quite common. You might have learned about pyruvic acids in your biochemistry class, or pyruvate, or actually lactate would be a more common version of this, lactic acid. This is a pretty common functional group. And the way you make this is you hydrolyze this under just brutally strong conditions. You use hydrochloric acid, but you need way more than one equivalent to get the reaction to go quickly. To drive the reaction stoichiometry, you need to add HCl, but to get it to go fast, you need super high concentrations, 6 molar hydrochloric acid. That's like taking a bottle of concentrated HCl and diluting it 1-to-1 so it's half concentrated. Still scary concentrations. 6 molar hydrochloric acid, it's aqueous. And you need the water because you can see there's oxygen atoms in the product. And if you don't boil this overnight, it'll never work. If I ask you to do this, you don't have to show the concentration. Let me just put brackets around that to indicate that. But I would expect you to write HCl. You need an powerful acid catalyst. H2O, because there's oxygens in the product. And I expect you to show heat. You don't have to show 100 degrees. You could show a delta symbol. But you have to boil these things. Crazy harsh conditions to hydrolyze this all the way. Don't worry about the mechanism. The book doesn't show you the mechanism. You're not ready to think about the mechanism until the next chapter. So let's just set that aside. But I expect you to know this pattern of reactivity, that anytime you have some sort of a cyanohydrin group, it doesn't matter where you got it from. I'm trying to switch to a black pen here to draw this out. Anytime you have some sort of a cyanohydrin group, OH, C triple bond, and it doesn't have to be a cyanohydrin. It could just be a cyano group. You don't need the OH molecule there. Then you can hydrolyze this using HCl, H2O, concentrated HCl, like not just one equivalent of HCl. And let me just write a delta symbol there to show that you don't have to memorize the 100 degrees, but I want you to know how that you're boiling this. There's my Greek delta symbol. And that'll convert any nitrile into a carboxylic acid. I'll put the carbonyl going down. That's called Mendelic acid, that particular carboxylic acid. Okay, so that's a pretty common functional group, a hydroxy group next to a carboxylic acid. We're going to have a whole chapter on carboxylic acid derivatives and nitriles. I think in the 6th edition of the Gorzynski-Smith textbook, they might have moved the nitriles into a different chapter. So I'd have, but it kind of belongs with carbonyl derivatives. Okay, so we're going to talk about another carbon-carbon bond forming reaction that does not really belong in this chapter, but it's clear that the author didn't know what to do with this reaction. But it's such a useful and powerful reaction. They do a version of this Wittig reaction in the organic chemistry laboratories here at UC Irvine. So I'm going to show you a reaction that allows you to take CO pi bonds and change them into CC pi bonds. It's kind of like the opposite of ozonolysis. And I'm going to show you a secret reagent here called the Wittig reagent that allows you to do this. So if you have a carbonyl and you want to convert that into an alkene, I'll just put an R group here. Who cares what the R group is? Then we have a reagent that we can use to do that. And the reagent is, let me go ahead and draw it out for you. It's this spooky looking thing that has 3 phenols and a phosphonium. And there's a plus on the phosphorus, is one way to represent this. And then over here, we have a carbon atom that's nucleophilic. I'll go ahead and draw the lone pair there. You don't have to draw it, but that's going to be the nucleophilic end. And attached to that carbon is 2 groups. In this case, it would be CHR, and I'm running out of room there. You can kind of see that CHR. Let me draw the H over here. So if you take a ketone or an aldehyde, not an ester, not an amide, a ketone or an aldehyde, you can form CC double bonds from those. Now, the problem is we don't get good stereo control here. We end up with a mixture of isomers. This particular one that I've drawn here has the E configuration at Gagan. We're also going to get the Z isomer, the other double bond isomer. And so let me go ahead and draw that other product. Those are not the same products. They are stereoisomers. I expect you to recognize stereochemistry when you draw out products. So in this case, that's like the worst looking Z ever. But I don't know if I can actually fix that, but that's a Z. So you get both products in this reaction. Since I drew the H on one of them, let me draw the H on the other. So you can make CC double bonds. And if you did an ozonolysis on this, you would get back this 2-butanone product, this ketone product. The other byproduct of the reaction that people don't care about, we throw it away when we get it, is the P double bond O left over from the reagent. I'll go ahead and draw that for you. This leftover, it's a byproduct for the reaction. So at the same time that we form this, let me draw it the other way around here. Let me put the oxygen on top. So you get this thing called a triphenylphosphine oxide. So what happens to the phosphorus part of the reagent? Well, it forms this useless trash that we throw away into the organic waste. When we use this reaction, we care about the carbon-carbon double bond products or product. Now that's kind of inconvenient to end up with a mixture of E and Z isomers. You have to separate those chromatographically and then pick the one you want to work with and do more transformations like epoxidation or dihydroxylation or something else. So how do you avoid getting two isomers? Well, if you carefully pick your substrates, if you only apply it to substrates or reagents where there's some symmetry, you only get one product. So let me give you an example. Let's suppose I take a ketone where both substituents on the ketone are the same. Here's acetone. That's an example. There's a methyl on one side and a methyl on the other. And so if I do this Wittig reaction, let me draw this reagent out, PH3P plus, and then I've got the nucleophilic carbon atom. In this case, I'll have an H and a phenyl on the nucleophilic carbon atom. And now the product of this reaction would have, one of the products would be this. The other product would have the phenyl where the H is and the H where the phenyl is. But because on the other side of the ketone, because these two groups are the same, there's no such thing as E versus Z isomers. The two isomers are non-distinguishable. So you only get one product. This would be a great place to apply the Wittig reaction because you won't end up with a mixture of stereoisomers out of that. Let me give you another example of an application of the Wittig reaction that would be more common than the lame case I showed you up above that gives two isomers. If I took a ketone that was not symmetrical, then if I'm careful about this, I can do a Wittig reaction to make a CC double bond. And if I use a Wittig reagent that is got two of the same groups on the carbon atom, here's my Wittig reagent, then I'll only end up with one isomer. So instead of having an H and a phenyl on the Wittig reagent, I'm going to have two H's. I like to see that carbanion there just because it reminds me that that carbon is nucleophilic. We'll talk about the mechanism shortly. So when I apply this Wittig reaction to the carbonyl, there it is, that's the product. And I don't have to worry about getting E and Z isomers there because the two substituents on this alkene are the same. There they are. Those are the same substituents. We don't, right? So that's a great way to apply the Wittig reaction. So if you're very careful about how you apply it, I'm usually careful about how I use the Wittig reaction in the laboratory. You can avoid getting E and Z isomers. Otherwise, if you start with unsymmetrical ketones that have ethyl or methyl or phenyl or different things on each side, and an unsymmetrical Wittig reagent, you're going to get mixtures of E and Z isomers. And I would expect you to recognize that. I always expect you to recognize stereochemistry. Now, notice if I had drawn out all these phenyl groups, each one of those is a 6-carbon ring. There's like 18 extra carbons in this triphenylphosphine moiety in that triphenylphosphine group. And it might help you to draw those out at some point because in sapling, well, sapling actually allows you to abbreviate phenyl groups as pH. So, but you can imagine how complex that structure is if you draw out all 3 of the phenyl rings. So you might notice that I'm abbreviating it as pH3 phenyl just because it's so clumsy to draw that thing out. But I expect you to know that there's 3 phenols attached to a phosphorus. And when I took organic chemistry years ago, I used to get confused. It's like, wow, look at all those letter P's in there. There's P's on the phenol, there's P's on the phosphorus. You just have to recognize there's a phosphorus atom with 3 phenyl groups attached, 1, 2, 3, and there's a phosphorus atom in the middle. Don't mess up the molecular formula. Make it clear that you understand there's a phosphorus atom and 3 phenyl groups. And if you don't understand, then draw out the phenyl groups, which involve carbon atoms. Okay, let's go and think about mechanistically what's going on with this Wittig reagent. It seems so mysterious. I'm going to go ahead and draw out um, this Wittig reagent in a little more detail. I'll try to draw all the bonds here on the key components. So remember, there's three benzene rings, three phenyl groups attached to this phosphorus atom. I'm not going to draw them out, but maybe you can take the time to draw them out. Wouldn't that be a great exercise, drawing benzene rings? And there's going to be two substituents, not three. And I'll take the case where one of them is an H. You could have two different R groups on there if you wanted. And so the way I've been drawing it for you above those arrows is where you have P plus on the phosphorus, a formal positive charge, and a formal negative charge on the carbon with a carbanion. There's a lone pair on that carbon that's nucleophilic. Now, you may think, boy, it would feel really good if I could attack that phosphorus. And we can draw a resonance structure. In fact, this is a common resonance structure for people to draw. So let's go ahead and draw that resonance structure where we put a double bond between the carbon and the phosphorus. This is a perfectly legitimate resonance structure. It's not the best resonance structure because once you get down below the second row, once you get down below the second row atoms, carbon, nitrogen, oxygen are great at forming double bonds. Nothing else below that row is good at forming double bonds. The atoms are too far apart. The double bonds are always weak. And so, right, if I were to compare this, I'd say this is a better resonance structure. This phosphorus carbon pi bond is so weak, and it actually helps you to draw this other form. Whenever you have two atoms that are next to each other, or one is plus and one is minus, we refer to that as an ylide. That when you've got plus and minus atoms next to each other, that's called an ylide. And that carbon acts like a carbanion. It wants to attack carbonyls. So again, if you're not familiar with what's phosphorus and where is it in the periodic table, it's right below nitrogen. It's a third row atom. Okay, so where do we get these Wittig reagents, these ylides, these phosphonium ylides from? Like a Wittig reagent. Well, we make them in the lab. You can't buy them. Well, you can't buy some of the ones that I'm showing you here. There's a few that you could probably purchase. Okay, let me come back to this, how you make a phosphonium ylide. Phosphonium, onium means there's a plus charge on the phosphorus, if you want to know that word phosphonium. So you can buy bucketfuls of triphenylphosphine. My gosh, that stuff is so cheap and inexpensive. And there's a lone pair on the phosphorus. It's like an amine, except that lone pair is more nucleophilic than the comparable nitrogen atom, than triphenylamine. Because as you go lower in the periodic table, things become more nucleophilic. So that becomes very good at attacking and doing SN2 reactions. So let me draw a substrate for doing SN2 reactions. I'll draw a partial structure for an alkyl halide. In this case, I'll have an iodide on there. That's you learn to push those out through SN2 reactions using leaving groups. Now, you typically have to heat these. It's not a great process in most cases. Maybe methyl iodide would be reactive enough where you wouldn't have to heat it. So this is going to undergo an SN2 reaction. You already know SN2 reactions. What else could you have as a leaving group? You could have bromide. You could have tosylate. You should know that kind of SN2 chemistry. And even if you didn't see SN2 reactions with phosphorus, I wish they'd shown you that back in the first quarter of organic chemistry. I'm sure they didn't. It's one of the few useful SN2 processes that they could have shown you. And so this will make a bond between the phosphorus and the carbon atom. Let me go ahead and draw that out. Here's the phosphorus atom. I'll draw out the phosphorus atom. There it is. And we're going to have those three phenols. I'm just going to draw it as a molecular formula because we don't really care about those three phenyl groups on the phosphorus. If I make a fourth bond to that phosphorus, I have to put a positive charge on there. I can't just, right? If it was neutral before and I make a fourth bond, it needs a positive charge. And then here's that CH2 group over here. And here's the R. I just did an SN2 reaction. Oh, we can't just have one positive charge in the products. We have to balance that out because our starting materials were neutral. And the other byproduct for this salt you get is an iodide. So the product you get is a triphenylphosphonium iodide salt. And you've got a phosphorus carbon bond. Now, if we want to make an ylide, we have to deprotonate the carbon. And there's one and only one base that is going to do that. And you've never seen it used as a base before on purpose. It's butylithium. You've seen butylithium or alkylithiums used for addition to carbon-carbon bonds. Every single laboratory here at UC Irvine, every organic laboratory has butylithium, a bottle of butylithium solution sitting around. And again, when you see alkylithiums, you'd like to use them to add to carbonyl groups. And I'm just going to write italics N butyl lithium. That's butylithium. It's just 4 carbons with a carbon-lithium bond. And that carbon-lithium bond, if there's no carbonyls around, it's going to deprotonate this CH. You can't use sodium hydroxide. You can't use potassium T-butoxide. You've got to use butylithium. You need a powerful. And so that deprotonates one of these H's. And I can draw this as the P plus form with the carbon minus. But instead, I'm simply going to draw this. I'll draw that with the CH double bond. But again, I could have drawn it as I did above here with P plus carbon minus. But instead, I'm going to draw the P double bond C form because it's just kind of easier to draw right now. So that's the 2-step synthesis of a phosphonium ylide. And I'm drawing the double bond resonance structure of the phosphonium ylide, which is actually a pretty common way to depict those. And man, that one thing wants to react with carbonyls in ketones and aldehydes. Not esters, but ketones and aldehydes. Give me one, because I want to add to that to make a CC double bond. It's so irresistible. Let's walk through the mechanism for this Wittig reaction. Let me draw a carbonyl compound that has the same groups on each side. I'm going to pick a ketone. This one is called benzophenone. I'm going to draw the C atom of the ketone. That's called benzophenone. It's a ketone. It's got the same group on both sides, so I don't have to worry about stereochemistry. And I'm going to take the simplest possible Wittig reagent, simplest possible phosphonium ylide. That would be a phosphorus with 3. Let me draw the bonds. Normally I don't draw these bonds, but I'm scared you're going to forget that this PH3P group has 3 phenyl groups on a phosphorus. So I could use the double bond resonance structure or the ylide resonance structure with a plus and minus. I'm going to use the ylide one. So we can really see that carbon is nucleophilic. Carbon, not the phosphorus, the carbon is nucleophilic and wants to attack that carbonyl group. So let's go ahead and draw out that arrow pushing mechanism where that ylide adds to the carbonyl. So as you push the electrons from the carbanion carbon into the carbonyl group, we're going to break the CO pi bond. We're going to break the CO pi bond, but we're not going, don't do this, don't draw that arrow right there. Because as you're attacking the carbonyl group, the double bond from the carbonyl will come back and attack the phosphorus. And I'm pretty sure you're not going to see any other mechanism where that happens. You're not going to see any other mechanism where as you're attacking the carbonyl group attacks a proton or does some other thing. So I want you to recognize that this is exceptional. In this particular reaction, it is concerted. You form, at the same time you're adding to the carbonyl, the carbonyl is attacking something else. Don't think that that's general. Don't do that on other mechanisms. This is a special mechanism here where we're doing that. And you end up with this 4-membered ring that's going to stress you out. I think it would stress me out if I hadn't seen it a million times. So you get this 4-membered ring where the oxygen is now bonded to the phosphorus. Get ready, you're going to freak out even more. And that CH2 group has now formed a carbon-carbon bond. And now the thing that's going to freak you out is there's 5 bonds to the phosphorus atom. And you're going to think, my God, I've never seen 5 bonds to phosphorus before. That's the weirdest thing ever. No, it's not weird. Of course you've seen 5 bonds to phosphorus. Go look at any DNA molecule. Every single nucleotide phosphate group has 5 bonds to phosphorus. Go back and look at the reagent for POCl3 that you used back in the first quarter of organic chemistry, or maybe the second quarter, and that has 5 bonds to phosphorus. So it's not weird to have 5 bonds to phosphorus. Phosphorus is not a second row atom, right? It's second row atoms where you're kind of limited to 4 bonds, except in very exceptional cases that you haven't learned about. But 5 bonds to phosphorus is no problem. 6 bonds to sulfur, no problem. Those are not second row atoms, they're third row atoms. Whenever you have 5 bonds to phosphorus, we call that that kind of functional group. How do I do this without messing up my structure? 5 bonds to phosphorus, 5 single bonds is called a phosphorane. I can't, wow, I'm not, how do I get that on there without overlapping on my, I'll draw it in small letters. Phosphorane. You can buy chemical reagents where there's 5 bonds to phosphorus. PCl5 is commercially available. So don't freak out over that. I realize it's hard not to freak out because you haven't seen that before. So the next step of this 2-step mechanism, this is all happening in one pot. You can't stop this. You can't isolate this intermediate. Let me put some brackets around this to just indicate that this phosphorane intermediate, it just kind of forms and immediately falls apart. You can't stop it from falling apart. You don't have to do anything extra to make it fall apart. Let's go and draw the arrow pushing mechanism for making this fall apart. And what we're going to do is we're going to make a super stable phosphorus oxygen bond. There's a huge, and notice how I'm making the arrow end on the phosphorus atom instead of on the bond, because this online homework system we use, we have to do that. We have to make the arrows end on atoms instead of right in the middle of bonds. And at the same time that we're taking electrons away from this carbon atom, we're using the electrons in this phosphorus carbon bond to attack back over here. And so that makes a CC double bond. That's how we end up with a CC double bond in our product. So that's the 2-step mechanism, arrow pushing mechanism for a Wittig reaction. There's no intermediate that you can isolate. This intermediate 4-membered ring is not stable. You couldn't isolate that. And the byproduct has this amazingly stable, love it. Oh, love that phosphorus oxygen bond, the phosphorus oxygen double bond. And nature loves that too. That's why DNA is made out of phosphorus, phosphate functional groups. Every single nucleotide subunit in your 9 billion base pairs, or in your 10 to the 9, 3 billion base pairs is made out of a phosphorus with 5 bonds with a PO double bond. Super stable. Okay, so the one thing to remember is that this is a reaction for aldehydes and ketones. It doesn't work with esters. So let me give you an example. If I took phenyl here with a carbonyl and I had an oxygen attached to that, so instead of a ketone or an aldehyde, if I had an ester, I'll just pick a methyl ester in this case, this reaction won't work. You won't get any reaction out of here. We'll find out when we start to rank things in the next chapter that when you take pH, that triphenylphosphine group is not well drawn. So let me try to do a better job of drawing that. If I take some sort of a phosphorus ylide and I try to add it to an ester, whoa, that almost looks like don't do that. Don't put a positive on that methyl. The positive goes in the phosphorus. And I try to add a Wittig reagent to that, you don't get any reaction. It's like, no, it doesn't work. You're just not going to get any addition. So don't try to make CC double bonds from esters using the Wittig reagent. I'll just write, no, don't do that. It's not going to work. Okay, Wittig reaction. Get an aldehyde or a ketone, you can convert it into a double bond. And if you had a CC double bond like this one over here, you could ozonalize it back to a ketone. Now, I want to show you strategically how to think about using the Wittig reaction. And the book is really big on this idea of strategy. If I told you to construct this using any kind of chemistry you want, I hope you recognize that we could use the Wittig reaction for this. So if I took cyclohexanone, which is a super common starting material, super inexpensive starting material in organic chemistry, you could use the Wittig reaction to construct that, right? If I didn't tell you what you had to use but suppose I told you you have to use cyclohexanone to make this. The easiest way to make this would be to do a Wittig reaction. There we go. And in this case, I'm simply going to draw the resonance structure of my Wittig reagent that has a P carbon double bond. That's it, and we're done. Now, I hope also that you remember from the last chapter, but wait, didn't Dave tell me that we have these very powerful alkylithiums and Grignard reagents for making carbon-carbon bonds? That would be great if you remembered that. You can see I'm adding a 2-carbon piece, and so why not do this in a slightly longer route? Why not add some 2-carbon piece like an alkylithium, step 1, and then in step 2, we would do an aqueous workup. All right, step 2 is water. You don't mix them together. If you leave out the 1 and the 2, step 1, step 2, if you don't enumerate the steps, that's wrong. Ethyl lithium plus water simply protonates the ethyl lithium. Now, the product of that would be a tertiary alcohol. Right? That's what would happen if you added ethyl lithium or ethyl magnesium bromide to the ketone. And in theory, you could dehydrate that to make an alkene. There's all kinds of reagents that you used. POCl3 and pyridine, or probably H2SO4 is a more common uh, condition for elimination. You protonate the, I'm not going to draw all the mechanistic steps, but you protonate the OH and make a leaving group, and it pops off to give a carbocation. And then something picks off a proton to complete the E1 elimination mechanism. But the problem with that is if you do that, you're also going to get another product in there that we don't want. You can't, once you form the carbocation, you'll also get another alkene, whether you want it or not. And that's not efficient. You can't stop it from eliminating into the ring, right? If I draw out all the protons, there's protons here, there's protons here, there's protons here, you can't stop all these possible eliminations from occurring in this case. So you would not want to do this two-step mechanism. You would want to use the Wittig reaction. Now, in theory, there's another approach to do the Wittig reaction. It's not quite as efficient. So let me go ahead and draw out this alternative synthesis of this product that would involve a Wittig reaction. It would involve taking this Wittig reagent and then taking a different aldehyde. So you would take this other aldehyde here and do a Wittig reaction. Well, that's fine. The problem is it's just not easy to make that Wittig reagent. If you had it in your hands, that would be great, but it's not easy to make that. And let's walk backwards through the synthesis of that Wittig reagent and see why that's kind of a difficult thing to do. And the reason is that that's difficult to do is that well, there's no problem with deprotonating this phosphonium salt, right? You would make this through deprotonation. I already told you the two-step mechanism for synthesizing. I'll draw the proton right there. Remember the base I told you have to use, to make a Wittig reagent? It's butyllithium. So no problem with deprotonating that salt. And the counterion here could be whatever. Actually, let me draw that in just a second. Where do you get phosphonium salts? The problem is you have to make these through SN2 reactions. And even in our most optimistic scenario here, the most optimistic scenario that we could have, if we made this through some sort of an SN2 process, we're kind of stuck trying to do an SN2 reaction on a secondary alkyl halide. And that's just not a good reaction. In fact, let me try to erase this if I can. Erase that arrow there just to remind you that's not really a very good process. SN2 reactions on secondary alkyl halides, and let me just remind you that would be SN2. If you tried to do an SN2 reaction on a secondary alkyl halide, you've got all this problem of having plus E2 eliminate, plus E2 competing E2 elimination reactions. So you get some of this phosphonium iodide salt, and it's not like you can use a better leaving group. That's just going to give you more E2 also. So you can't win here if you're trying to make this this cyclohexylidine phosphorane Wittig reagent. Really, the best route here, the most efficient route for doing the Wittig reaction. Let me just go ahead and indicate this in red here. This would be the best route because it's easy to make this. It would be easy to make the synthetic reagent, this phosphorus ylide reagent. You wouldn't have any problems doing an SN2 on a primary alkyl halide. Wouldn't lead to any problems. Okay, and again, if you wanted to take your cyclohexanone and try to convert it to this cyclohexyl iodide, that's just more steps to the root. Okay, as we go on in this class, you're going to have a lot of reactions. We're going to keep teaching you new reactions that increase the number of ways that you can make things, but you got to pick the best way, or be able to think about strategies for doing things the best way. All right. Now, the last thing we're going to cover is the reaction of amines today. At least the last thing we're going to cover is what about nitrogen nucleophiles? I've talked about cyanide anion, adding HCN across ketones and aldehydes to make cyanohydrins. We've just spent quite a bit of time talking about the Wittig reaction. And let's go ahead and talk about forming bonds between aldehydes and ketones and nitrogen. And I'm going to break this up into, first I'm going to talk about primary amines, and then I'm going to talk about secondary amines, because you get different products depending on the structure of the aldehyde or ketone and depending on the amine. So let's go ahead and take an example with RNH2, where there's two H's on the nitrogen. I'm going to, let me go ahead and start off here with just benzaldehyde. It's kind of a simple, common carbonyl compound. Actually, I've done this reaction in the lab. What a feel-good reaction. You just mix things together. Whoops, that should be CH3. So methylamine and benzaldehyde, and you mix them together. And we're going to add a catalyst here. And the book says weak acid. And it's so secret, they don't want to tell you what the acid is. I don't get it. The acid is acetic acid. It's not such a secret, and it's not hydrochloric acid. That's a strong mineral acid. It's not sulfuric acid. That's a strong acid. It's not toluene sulfonic acid. That's a strong acid. It's just acetic acid. So let me go ahead and draw it out. I'll kind of draw out a formula here. But quite often we write out acetic acid like this, CH3CO2H, right? That's a common way to write it out as a text formula. Now, when you do this reaction, you condense. That means you give off water. Anytime you hear the word condense, it means the byproduct is water. So the byproduct of this reaction is going to start with a double bond O, and you'll finish up with a double bond N. It's kind of like the Wittig reaction transformation in a way. You know, if you did a Wittig reaction on this, you'd end up with a carbon-oxygen double bond. In this case, we end up with a carbon-oxygen or carbon-nitrogen double bond, and the byproduct is water. So that turns out to be a very efficient process in this case. Let me go ahead and so let's just to make sure we've got this reaction transformation down, let's take another carbonyl compound, either an aldehyde or ketone. So not an amide, not an ester, and let's take another amine. In this case, I'll take aniline. You know how to make aniline. You nitrate a benzene ring, and then you reduce the nitro group down. So, wow. It's like we're just learning more and more reactions where you know how not only to do the reactions, but you know how to make the pieces for the reaction. And we're going to add a catalytic acid here. Don't write weak acid. If I ask you for a reagent, there's no bottle of weak acid sitting on our shelves. We have bottles of acetic acid. You can buy acetic acid in the store, except it's as vinegar, but it's got water in it. I'll just draw out the molecular formula here. CH3CO2H. Some people forget to draw the C from the carboxylic acid when they write out the molecular formula for, or this text formula for acetic acid. So remember, there's two carbons in acetic acid. So the product of this reaction would have a carbon-nitrogen double bond. Let's go ahead and draw that out. And there we go. I'm not going to draw out the phenyl ring. I'll just write pH there. So you take either a ketone or an aldehyde, and you add an amine that has two H's on there. This is a primary amine. We're going to have a whole chapter on amines. And this phrase primary, that means there's two H's on the amine. And the other thing attached to the amine would be an aromatic group or an alkyl group, not a carbonyl. That's called an amide if there's a carbonyl group directly attached to the amine. Okay, and you get the water as a byproduct. I'll just kind of write it in a different color here because right, if I ask you to draw the products on a problem set or on an exam, you know, I don't want to see the water byproduct. I usually say draw the organic products. Organic means it contains carbon. We don't isolate the water and save it like it's some precious thing for an organic reaction. We're focused on the things that contain carbon. So again, since water contains no carbon atoms, we usually don't write that byproduct. It's not really particularly relevant. Okay, so we've got this imine formation. Let's see how much of the mechanism we can get through here to understand what's going on. The mechanism for this reaction involves the nitrogen attacking the aldehyde. I'm going to draw out a 6-step mechanism. Let me do this using this, draw the structures using the black pen. And in this case, I'm going to pick the version where I start with aniline. There's pair of electrons on that aniline, and we're going to attack an aldehyde. In this case, I'm going to make it acetaldehyde. Let me go ahead and draw that group there. Okay, we're going to start off the reaction. Guess how? We're going to attack the carbonyl group. There we go. And you might think, well, gee, if it's run in acetic acid or any acid or an acid catalyst, I have to use the acid on the first step. Well, this is tricky. It's a weak acid. And the aniline, the amine, gets it some of it gets protonated, but under the conditions of the reaction, because you're only using catalytic acid, there's enough nitrogen lone pairs in there that you can directly attack the carbonyl and without using acid in the first step. So let me go ahead and draw this next intermediate that we get in this reaction. It's going to have this new nitrogen carbon bond. There's an H on that aldehyde. I'll draw it in there. And there's our O minus that we get by kicking electrons up to the CO pi bond. And I've still got 4 bonds to this nitrogen atom. And so we end up with this tetrahedral intermediate. Now, this is one of the 2 steps where the acid comes into play with that O minus there. If we've got slightly acidic conditions because we used weak acid, and I'm not going to draw out the acetic acid for an arrow pushing mechanism, we're just going to symbolize any acidic species that transfers protons as HA. Right? We don't care whether it's acetic acid that's transferring the proton or an ammonium group. That's just not really relevant, or we just want to focus on the fact that we're protonating that O minus with something. And you have to memorize the order of these steps. So let me go ahead and draw out the next intermediate here. It's going to have still have this ammonium ion on there. But now our OH group, did that just turn into a straight single bond? Something just happened there that I need to learn more about for this notability app. Okay, so now I've got this protonated OH, but I've still got my counter ion here with that lone pair. And so now we're going to deprotonate that ammonium ion using our A minus, the conjugate base that is left over from our acid. So let me pull that proton off. There we go. I'll give the electrons to the N plus. And so the next intermediate in my mechanism is now a neutral tetrahedral intermediate. And it even has a name associated with it. You'll see this mechanism enough in organic chemistry that when you have this hydroxyl group and an amino group on the same carbon atom, we call that a carbonylamine. It's not a stable functional group. But I'll write out the name in case I use that name later. This is called a carbonyl amine. And now, this next step is really what that weak acid is all about. If you use a strong acid, you're simply going to, if you use sulfuric acid in this, you'd simply protonate all your amine, and there wouldn't be any acid left. So this is why we use a weak acid. But you need the weak acid for this next step here. You can't use a strong acid because it would simply protonate all your starting amine. But we use a weak acid here. And let me go ahead and draw the symbolic version of that acid. And this is where that weak acid plays its critical role, is we have to get the acid to protonate our leaving group. And our leaving group is going to be water. So we have to protonate the OH to turn it into a good leaving group. And so now we're going to be ready to form that carbon-nitrogen double bond. We've got a water leaving group now. And unlike all the SN1 chemistry that you learned about with water acting as a leaving group to make carbocations, I want you to draw this lone pair on nitrogen, because this is going to be something you're going to see over and over again in the future. That lone pair, it's not just that the water is going to leave and make a carbocation. No, it's going to get pushed out. The neighboring lone pair, and you're going to see this over and over, is going to push out the leaving group. Pushes it out. That's better than any SN2 displacement you've ever seen before. You've got a good leaving group there, but the lone pairs that are right next door will push that leaving group out. Get ready to see that over and over. The neighboring lone pair is going to push out that leaving group. And so we end up with our CN double bond. It still has a proton on there. I'll draw the bond because we're about to deprotonate that This species is a super important species. It's so important. I'm going to draw in red letters the name of this species. And I've referred to it up above. This species is called an iminium ion. It's one of the most important functional groups in biology. It's one of the most important functional groups in organic chemistry. And for this mechanism, we're going to deprotonate the nitrogen of this iminium ion intermediate. So remember, I still have that A- floating around from the previous 2 steps. I'm going to deprotonate that iminium ion to make a neutral imine. That's the product for this reaction. Is that the lone pairs stay on nitrogen here. I'm making that clear. And so now the product of the reaction is the neutral imine. That may seem exhausting to you. Look at all those steps. It's a 6-step mechanism, but that's pretty typical for this chapter and for the next chapter. We're going to have a lot of 6-step mechanisms. Okay, so that's the mechanism for formation of an imine. And if I gave you an imine and I said, here's an imine and there's acid and there's water, lots of water to drive the equilibrium back in the other direction, you would draw the same intermediates for the backwards mechanism. It's the arrows that would change, but the intermediates would be the same. Okay, when we come back on Wednesday, we're going to hear about another type of product that you get by mixing amines with aldehydes and ketones. But in that case, it would be secondary amines that have only one NH bond, and they give a function group called enamines. So, okay, we're in a chapter where we're using most of this chapter. The rest of this chapter is going to be adding weaker nucleophiles like nitrogen and oxygen to carbonyl groups. So when we come back, we're not quite done with amines condensing with aldehydes and ketones. We're still going to keep working on that. So stay safe, stay sane, and beyond that, staying safe and sane, focus on the organic chemistry, practice the mechanisms, work on the problem sets, work problems out of the textbook. Every chance you get to try to apply these reactions that you're learning to synthesis problems, to think about the mechanism, take advantage of that. And thanks for sticking with our course here. Again, I'm telling you about the stuff I love, which is organic chemistry and mechanisms and reactions, and keep going, you guys.
This is David Van Vranken here at UC Irvine. There seems to be some sort of a fire east of here because the Santa Ana winds are blowing from the east off of the deserts, and those strong wind conditions create an extreme fire hazard due to the dry brush and dry vegetation here. You know, the clouds are filled with smoke that's being blown in from the deserts to the ocean, and the thing that's scary here is that there's ashes in the air that keep flying into my eyes. They're cold ashes, but if there's cold ashes here, that means there's hot embers flying somewhere else ready to spread the fire. So, hope you're staying safe.
The man would die when you made the constant dry, when you made it so that it could not get not another drop of rye. But I know that you will feel bad when you see what he have had, when you see him coming with a lot of talk. If you're listening, I will tell you folks, oh well, it's here he comes. I mean to tell you, here he comes. He's got those J's lay on the leg blue. Here he comes. I mean to tell you, here he comes. He's got those J's lay on the leg blue. When you see him coming, I am going to tell you, if you sell him Jake, you better give him a price too. Oh well, it's here he comes. I mean to tell you, here he comes. He's got those J's lay on the leg blue. Oh, step on it. I mean to tell you, here he comes. He's got those J's, leg blue. Here he comes. I mean to tell you, here he comes. He's got those J's, leg blue. He could be named Charlie and he could be named Ned, but if he drank this Jake, it will give him the leg. Oh well, it's here he comes. I mean to tell you, here he comes. He's got those J's, leg blue.